Object-oriented programming relies on a highly convincing, yet fundamentally flawed, high-level illusion that hides the physical reality of the machine. You write these two lines to create an object and call its method. The standard mental model treats the object D as a physical container holding its methods inside it, with self acting as a variable passed between them. Look closer at the runtime memory, and that container vanishes. There is no method inside an object, and Python is not passing objects around in memory. This high-level view of syntax limits your understanding of how code actually interacts with hardware. Breaking that limit requires seeing the true runtime system. We are going to trace the exact physical pipeline of that single line of code, d.bark, down to the bare metal. To do this, we need to track three distinct physical environments: heap memory, where long-lived objects are stored; the execution frame, which holds local variables for active processes; and the CPU registers, the hardware's immediate workspace. We are stepping past the high-level illusion of code running to watch the physical reality: memory moving, pointers flowing, and the CPU executing. Tracking this specific sequence is the dividing line between writing Python and engineering the systems that run it. Let's look at the initial resting state of the system before .bark is ever executed. This diagram shows our three memory environments. First, Python allocates memory in the bottom heap pane for the dog class itself, mapped here to hex address 0x1000. Next, the standalone bark function is loaded into memory. It resides at a completely different address, 0x2000. Finally, we create the specific instance D. It is allocated at a third address, 0x3000. If we deconstruct this instance, we see it only holds a reference count to track memory usage, a type pointer mapping back to the dog class at 0x1000, and the raw data. There are no functions inside this block. Because the function and the instance data are physically separated in memory, the system must build a bridge to connect them without duplicating that memory. The dot syntax in d.bark triggers an attribute access. In Python, this invokes the descriptor protocol, an internal mechanism that manages how object attributes are accessed, retrieved, or modified. This lookup searches the dog class's internal dictionary and locates the bark function. The runtime then creates a temporary structural bridge on the heap, the bound method object. The internal architecture of this bound method is strictly a pair of pointers. These pointers route directly to our existing memory addresses. The func pointer maps to the function at 0x2000, and the self pointer maps to the instance at 0x3000. This architecture eliminates the need to copy heavy objects. It simply pairs their existing memory addresses in preparation for execution. The parentheses in the call trigger a C-level command called pyObjectCall to begin execution. cpython immediately responds by constructing a temporary execution frame in the top right pane. cpython is the default reference implementation of the Python language written in C. This frame isolates the memory and variables for this specific process. Inside the frame is an array of local variables called flocals+. The first slot, slot 0, begins completely undefined. The runtime now unpacks the self pointer from the temporary bound method bridge we just built. That pointer is injected directly into slot 0 of the execution frame, overriding the undefined state with the address 0x3000. This specific injection event is the physical manifestation of self. It is a memory address mapped to an index slot. With the frame set up, the actual execution begins with a specific Python bytecode instruction, load fast 0. Bytecode is the low-level, platform-independent instruction set that the Python interpreter executes. This instruction commands the interpreter to look strictly at index 0 of the current active frame. Looking at the new hardware schematic below the frame, we see this translates down to its bare metal CPU equivalent, like the MOV instruction. The hardware physically reads the memory from the frame slot and loads that pointer into its active register. A register is a tiny, incredibly fast storage location built directly into the CPU. The CPU now uses the pointer residing in the register to access the target object's memory and run the method logic. Throughout this entire pipeline, the actual object instance D never moved from its spot on the heap. Only its address traveled. This complete map shows the continuous, interconnected system we just built. Let's trace it. Step 1. The pointer is stored in the heap memory. Step 2. The pointer is paired in the bound method bridge. Step 3. The pointer is injected into the execution frame slot. Step 4. The pointer is loaded into the CPU register. cpython operates as an engine for routing memory addresses through slots into hardware, bypassing the overhead of moving heavy objects. Why does this granular, hardware-level tracking of a simple Python method matter? Transitioning from syntax-level thinking to systems-level flows is a requirement for engineering at a massive scale. This same pointer routing logic is what allows machine learning frameworks to manipulate multi-gigabyte tensors. By passing memory addresses rather than duplicating the underlying data, these systems perform complex transformations without exhausting the hardware's RAM. The mechanics of execution frames and pointer injection are the core foundations used to build language interpreters and distributed task systems. Tracing the path from heap allocation to CPU register provides the technical context needed to understand how programming languages and high-performance systems are actually constructed.